that, I want to introduce Dr. Gary Fox, whom will introduce our next speaker. Dr. Fox is professor and Buchanan Endowed Chair at Oklahoma State University and also director of the Oklahoma Water Resources Center.
All right, so I get to introduce maybe not necessarily somebody that's as established as some of the other researchers, but I think it's also important that we hear from kind of the up-and-coming researchers in the field. And so I'm going to introduce Rachata, who goes by Chat. You heard Dr. Ronaldo refer to him already today, Muneepeerakul. Chat is originally from Thailand, did a Master's of Science from the University of California in Berkeley, and then did his PhD in Princeton in Civil and Environmental Engineering with somebody you've already heard about too, Ignacio Rodriguez Iturbe, who has worked in this field for a very long time. Chat was an assistant professor at Arizona State University and has recently, as of May, I believe, joined the Agricultural and Biological Engineering Department at the University of Florida. So this is an opportunity to hear from him and to welcome him to the Ag and Biological Engineering community. So, Chat.
Hello. Hello, everyone. Thanks a lot for inviting me here to participate in this interesting session. So today I would like to share with you some of my recent work on incorporating strategic behavior in ecohydrological models. And this is a work in collaboration with Dr. Marty Enderius at Arizona State University. Okay, as you have heard from the first few speakers, in the past few decades we have learned a lot from the field of ecohydrology, as the previous speakers have shown you, and as can be attested by some of these titles. Of course, your list of favorite ecohydrology books might be different than this, but there you go. But I would say that I think it's getting more and more difficult to find a system in which ecological and hydrological processes are left alone, interacting among one another without human intervention. And I think that has been increasingly recognized by some of the previous works like this. Now, a lot of these works are done by natural scientists or ecohydrologists. So they use ecohydrology as a starting point, and naturally, they try to preserve some of the ecological and hydrological details in their models. And at the same time, they want to keep their models simple, to make it parsimonious, to keep the relationships between many things clear, which is a good thing. But as a result of that, sometimes the interaction with humans are highly simplified. In some cases, they are characterized by only one or two tuning parameters. But as we know, human actions are more dynamic and more interactive. So what I'm about to present to you today can be thought of as an complementary perspective of approaching this problem from the other side, as opposed to start from the ecohydrology, the natural science side. I'm going to focus on the social dynamic side of this coupled system. And I really think that by approaching the system from different perspectives, we would be in a better position to balance different kinds of complexity in our models. And as I looked around, there was some conceptual framework that we can use as a starting point already. So this is a conceptual framework developed by Marty Enderius, Marco Jansen, and the late Lynn Ostrom, the Nobel laureate in economics in 2009. So in this framework, the ovals represent the social components of a system, and the rectangles represent the biophysical components of the system. So ecohydrology has contributed a lot in great details about the resource part in that box. But then when people move to considering coupled natural human system, they tend to focus on the resource and the human as the resource users. So just, let's see. The first two components there. But in reality, humans do not interact with the resources directly, they do so through some kind of infrastructure. And this infrastructure can be hard and soft. Let's take agricultural systems as an example. In that case, hard infrastructure might be dams or irrigation canals. Soft infrastructure might be institutions or rules that people have to follow so that things can run smoothly. Regardless of its being soft or hard, this infrastructure needs to be maintained regularly. But in a large society, usually not everyone is involved in maintaining such infrastructure, and there are a group of people who is responsible for that. So we're going to call those people public infrastructure providers, or PIPs. So basically, for me, I like this framework as a starting point because it highlights this infrastructure-related components that are important but are sometimes overlooked. But the problem is this framework has been proposed like more than 10 years ago, and its application has been either qualitative or ad hoc in nature. So what I hope to do is to systematically and mathematically operationalize this framework. And today I'm going to present to you some of the preliminary results and discuss some potential extensions. So basically, to give you an example of what this mathematically operationalizing this framework might look like. So let's get to it. Let's write down some equations to describe this system. So let me start with the state of public infrastructure, S. So now S, so here I use S to denote state of public infrastructure. Low S mean that the infrastructure is in bad condition. High S mean that the infrastructure is in good condition. Now, one important feature of many infrastructure is the threshold behavior. So let me give you an example. If, let's say in an agricultural system, if an irrigation canal system is broken and you need $10 million to fix it, but then you can get only $1 million, that doesn't mean that you get to use 10% of its capacity, because the thing is would still be broken. In that case, it requires some collective action to push the system above a certain threshold so that it can be functioning properly. So that's what I mean by threshold behavior. And as you know, once you start getting into, for those of you who are more familiar with the dynamical modeling, once you start adding nonlinear effects and threshold behavior, interesting things happen. So but that's what we have in most infrastructure. And to capture such threshold behavior, I use this simple piecewise linear function. So in that function, you have S on the x-axis, and on the y-axis, you have function f of S. So here it says that if S is low, meaning that the infrastructure wouldn't be producing anything. If S is above certain threshold, then it would be functioning at its full capacity. So F, basically, function F influences the ability of humans to extract the resources. And we're going to be making a reasonable assumption that this infrastructure faces constant depreciation or decay and would eventually collapse if it doesn't receive enough maintenance. So with that simple, with a few simple assumptions, we can write down the dynamical equation for S. Basically, it's a balance between the maintenance function and the decay function. And I will define the maintenance function soon. Next, the resource. Again, this is the part where ecohydrology has contributed a lot. But because I want to coming from the other side, I will keep the ecological and hydrological details at the minimum in this case. So right now, I'm just starting from something simple. I have some resource. In this case, you can think of it as water, natural inflow of water coming in, and a natural loss of the water going out. And right now, I just assume that it's proportional to the level of available resource. And of course, this is the part where it can get more complicated. And we have learned a lot from ecohydrology already, and this can be done in a much greater detail. But I'm keeping it simple for now because I want to focus on the social dynamic side of the problem. And then you have the extraction by humans through the infrastructure. That's why you have that function f of s there to show the role that is controlling the ability of human to extract the resource by the infrastructure. So so far we're done with the biophysical components of this framework. Now moving to the social components that I want to focus on. So here we have two types of social actors, the users and the public infrastructure providers. I'm going to be making a few assumptions because you need to do that to systematically operationalize this framework. So I'm going to make this assumption. First, the user have two strategies to choose from. They can work inside the system, making use of the infrastructure. Again, if you're going to use ag system as an example, they basically using the dams or irrigation system to use in their farming activities and things like that. They also have another opportunity to working outside the system. Again, farmers leave their villages to work in the city to earn some wage all the time. And you can think of W there as a wage. It's kind of outside incentive that would entice the farmers or the users to leave the system. But again, because in this system, public infrastructure providers are the ones who are responsible for maintaining the infrastructure, so not the user themselves. So the user have to give up a certain fraction of their income that they make from the system, and we're going to call that fraction C, to the public infrastructure providers, PIPs, and hope that they would maintain this infrastructure well. And this C is set by the PIPs. You can think of this C as some kind of tax or fee that the public infrastructure providers would charge the users to come and use their system and things like that. And there's another decision that the PIPs need to make. Now they get the total contribution from the users. They need to decide what fraction of that contributions they actually spend in investing in maintaining the public infrastructure, because they have other needs too. They need to keep certain of these contributions, say for their salaries. They might need to run some research projects or run some kind of awareness campaign. So they need to keep some to themselves, but they still need to spend enough to keep the infrastructure in their working order. And they too are subject to outside incentive. And I'm just going to use W sub P to represent that. Because if this system is not working very well, or it needs a lot to maintain, it doesn't produce a lot, maybe the public infrastructure providers may think, well, this is not worth our time and energy. Maybe we should spend our time and energy managing or maintaining other system instead, and they may leave. And with all those assumptions, I can write down I can use that function for the maintenance function, and now we complete the dynamical equation of how the state of public infrastructure might change through time. Now, so how should the social actors in our models make their decisions? I think for me that's the tricky part of trying to mathematize this framework. So for this, I refer to a recent paper by my colleague Marty NRES, in which he describes socio-ecological system as partially self-organizing and partially designed. So how would you mathematically operationalize concepts like that? So for me, right now, I came up with a simple characterization. So you see, a lot of the traditional economics model, they assume that people are very rational. They're thinking long-term, they're calculating, they're planning, they're optimizing all the time. So I'm going to relate that kind of optimization way of thinking to the design part of the statement on the top of the screen. Then there's another school of thought that say, yes, people are smart, but they're not extremely smart. Yes, they are rational, but they only boundedly rational. For example, you would be observing your friends, and a few of them might be doing something different, and they are doing better than you are. So you might decide to replicate what they are doing to improve your situation. So you are rational, but you don't have to be extremely smart to be copying or replicating what other people are doing. And that represents some kind of simple social learning mechanism. And luckily, there's a mathematical machinery to capture that kind of social learning mechanism already, and it's called replicator equations. So I'm going to relate these replicator equations to the self-organizing part of that description on top. So now we have a simple characterization that we can use to capture this self-organized, part self-organized, part designed system. But who's doing what? We have two types of social actors in our model. So I hope that you would agree with my further assumptions that because the users is in the public, and I think it's reasonable to say that they do not always engage in high planning and optimization all the time. So I would assume that the users go through this self-organization process through the social learning mechanism that I just mentioned. You know, they just look around, and if other people do that and they are doing better than I am, maybe I would replicate what they are doing. And therefore, we can write down the equation for U. This is U was the fraction of time that the user would spend working inside the system, and the rest of the time they might be working outside the system. So first, I write down the payoff function for the user. So you can see that it depends on the level of the resource R. And then you have that factor 1 minus C. Again, they have to give up some of their income to make the contributions to the public infrastructures whom they rely on maintaining the infrastructure that they need. And then what you have there is the du/dt equation. That's just the replicator equation. And then it has a relatively simple and straightforward interpretation. What that says is that U, the fraction of time that the users would spend working inside the system, would increase if working inside the system pays better than working outside. So that's kind of straightforward. And it would increase faster if there are already a lot of adopters of that strategy and potential replicators inside the system. So if you have a lot of both of them, then the replicator rate would be high and you would increase faster. Although simple in interpretation, it depending on how you define the payoff function, it could give very rich dynamics, this simple equation. And on the other hand, the other social actor in the system that we have is the public infrastructure providers. And here I envision this to be more of a formal or official organization, like maybe some kind of government agency that is tasked specifically to maintain certain public infrastructure. So I would assume that they involve in more planning. So I'm going to say that they go through this optimization process in their decision-making process. And that's their payoff function. So now you have the dynamics of the resource, dynamics of the state of public infrastructure, and these decision-making processes of the social actors interacting with one another. So the overall picture of this setup is this. So the public infrastructure providers would try to select C and Y. Again, C is the fraction of income that they would ask from the users to contribute, and Y is the fraction of the total contribution that they would actually invest in maintaining the public infrastructure. So you can think of these two things as the policy levers that they can turn. But at the same time, the users would self-organize to respond to those policies. You know, the public infrastructure providers may pick and announce that this is the C and Y that I'm gonna implement, but the users, through that replicator dynamics, would self-organize to respond to that, and their response would affect the infrastructure functionality and the resource availability. And it turns out that the preliminary results of this model can be captured quite nicely in this figure, but it has quite a lot of information, so I'm going to try to walk you through it. On the y-axis, you have C, again, the fraction that the public infrastructure provider would ask from the users. On the y-axis, you have Y, the fraction that the public infrastructure providers would actually invest in maintaining the infrastructure. So basically, these are the decision space of the public infrastructure providers. You have C and Y. These are the two policy levers that they can turn. And they can pick any point, but there would be consequences of their selection. So let's see what are the consequences. If you focus on the right portion of the figure, over there, C is high. What that means is that public infrastructure providers are asking too much from the user. You have to give me a lot if you want me to maintain the public infrastructure. And at that point, the users would say, well, that's too much, I better go work outside, and they did. So in that case, the whole infrastructure, the coupled infrastructure system would collapse. And that's why I call that vertical dash line user participation constraint. If C is too high, there would be no users participating in the system and it would collapse. Now, as C getting lower and lower, then more and more users would start to participate in the system. But that doesn't guarantee the survival of the couple system that we are interested in. Why? Because but even though the users agree to make the contributions, the public infrastructure providers need to invest enough in maintaining the infrastructure. In other words, Y has to be large enough. Otherwise, there's not going to be enough maintenance efforts to keep the thing going. How much? Then, because of the simple setting, we can calculate the exact condition of how much that should be, and that is represented by the black curve, which I call functioning infrastructure condition, meaning Y has to be greater than that, so that the public infrastructure can be maintained in a long run. But again, we have the social tension and social interaction because public infrastructure providers too are subject to outside incentive, meaning that if they have to invest so much in maintaining the infrastructure, they may say that, oh, this system is so demanding, it's not worth our efforts or energy or time. I should leave and go work with a different system. In other words, Y cannot be too high either to keep the public infrastructure providers happy. So how low it has to be? Again, we can derive that condition, and that is represented by the red line, which I call PIP participation constraints. So when you look at all these different conditions that capture these social interactions, you would see that in that decision space, there is only a small or limited region that I call sustainable region, in which everyone is sufficiently happy and the whole infrastructure system can be sustained in a long run. And again, I like this kind of simple setting because now the relationships between these interactions are clean. You can write it down in a few equations. Of course, it's still a little abstract, but I think by starting from something simple like this, we can build up our intuition, and then when you go back to the real complex problem, you have a better idea of how things might go, and then you can add more complexity on top. But I think it's good to start from somewhere simple. And already, I think that there are quite a bit of extensions that you can do from this process. So the first thing, I think, again, going back to ecohydrology, we have learned a lot from ecohydrology, but for me, personally, I think one key message that I get from ecohydrology is that fluctuation or stochasticity is important. And clearly, in this framework, I assume that you have a steady incoming of resources, water or whatever. But in reality, okay, those things can change. You know, the fluctuation in the resource availability, there may be some trends due to climate change. And also on top of that, there might be some fluctuating in the social driver. The outside opportunities might be fluctuating too. So what would happen then when those things fluctuate? This is what happened. So what we call sustainable region in that decision space can shrink or expand depending on the availability of the resource and the outside incentive. And now if you are the public infrastructure providers and you are so focused on maximizing your payoff, you might try to push your system in that point, let's say, try to push Y as low as possible. So you want to keep the thing going, but you want to keep a lot of the contributions to yourself. But if you do that, you put your system close to the boundary of the sustainable region. And when other factors fluctuate, then you would very quickly find your system located outside of that sustainable region. So, okay, over here, I use green star to say that things are fine, and I use, boom, red star there to say that things are unsustainable now. And you can see that if you stay too close to the boundary, you can turn red very quickly. But So if you want, so basically, if you focus too much on the performance, your system would not be robust against these fluctuations. If you want more robustness, you have to move further into the interior of that sustainable region, but then you would lose some of the performance of the system. But with this kind of simple setup, you can quantify that trade-off between efficiency or performance with robustness of the system. And I think that's something that has been kind of elusive. Robustness has been kind of a buzzword in a few years, but I don't think that there's a systematic way to kind of quantify it. And I think that this might be contributing to that attempt. So that's one possible extension. Another possible extension that I can think of is, what about different social structure? Because in that framework, they already made certain assumptions about the social structure inside the society. They already assume that the resource users and the public infrastructure providers are two separate entities. But that's not always the case. If you think of a lot of small-scale systems, like a small-scale farming system in developing countries, and that actually constitute a big fraction of agricultural production in the world. Those systems are small, like villagers in villages. And for that small society, you might not have that division of labor. Basically, the public infrastructure provider and the user may be coming from the same group of people, and then you have to modify your framework a little bit. Now, as opposed to have two types of social actors, you still have two types of social actor, but as opposed to have two groups, you have only one group of people having three strategies to choose from. And because of that change in social structure, the social tension and the social dilemma, even in the mathematical terms, would be different. And we can do that, and when we can compare the difference. So it has been my recent hobby to try to summarize my presentation in a rhyme. So let me give it a go here. So please bear with me. So I would say that in this work, we have ecosystem, water, humans systematically combined, interplays and dilemmas mathematically defined. Such systems are both designed and self-organized. With optimization and replication, they can be characterized. In a clear, simple model, these are made unambiguous. Important lessons are then brought to focus. Too much emphasis on just its performance, and the system would lose robust endurance. With some key dynamics on a sound mathematical grounds, interesting questions and extensions abound. Incorporate strategic behavior in ecohydrology. There is a lot of work we can expect to see. And as I was requested by Rafa as well, so I would like to close with this slide of some of the ideas of potential future research. I think I touched on a few points already. So we can include back, I kept the ecohydrology simple, but of course we can add more sophisticated and realistic ecohydrology back in. And anything really, I was using something really simple. I don't know, I think it would be very interesting to include something like biodiversity dynamics that Professor Rinaldo was talking about, or agricultural production and things like that, and see how the social tension and social dilemma change their characteristics. And again, we can study other social issues like free riding or asymmetry in access, especially in agricultural system when you have the upstream and downstream users. And I think we could, I would like to seek some input from practitioners in terms of model formulation. And lastly, it would be interesting to apply this framework to a wide variety of case studies, because this framework right now is simple and abstract, but at the same time is not so specific to a certain type of system. So I think it can be applied to a wide range of problems, and then you can do this cross-comparison for a very diverse set of case studies. And with that, I thank you for your attention.
From the audience? Anybody have a question? I know there are a set of diverse applications that we may be looking at in the state of Oklahoma that we want to talk to you about.
Okay.
So
Neat.
Hopefully you're going to lunch, because I want to talk to you at lunch, so.
First, I just really enjoyed your poem at the end. That was pretty awesome. On the graph, when you had C and Y, the threshold for C was 0.8, I believe. Is that like they're requesting 80% of the people's income for their utilities?
Can you say that again, please?
So the 0.8 threshold that you had?
Oh, no, that is not a universal number or anything. It's just a certain parameter set that I picked to illustrate the problem. So it really depends on the nature of your particular system. And then if you pick a certain threshold or ask expert opinions about the various quantity in the system, and then we can calculate that threshold. But it's not a universal number or anything.
Okay.
Yep.
Okay, because at 80%, it just seemed high to me, so I was wondering if you had a justification or if that was just an example.
No, yeah, it's just an example. Yep.
Okay, thank you.
Sure.
Great question.
Andrea.
Very interesting, Chad. Did you, can you define a little better how do you define the suitability region in the thing? How do you define the suitability region? Is it a stability problem or what?
Oh, no. So in that case, could you turn the presentation back on, please? Sorry. So no, that's just the intersection of different conditions that have to be met. So first, you have to have enough user to participate in your system. So you have to stay on the right of that dash line. And then you have to invest enough in maintaining the infrastructure. So you have to be on top of that black curve. And then you have to keep the public infrastructure providers happy enough, so you have to be below that red line. So it's the intersection of conditions that define that sustainable region. But as you see, as the resource fluctuates, sometimes that region squeezes into non-existence, and it means that that system is doomed. So, yeah. Okay. Good point. I'll think about that. Thank you, Andrea. Yep.
Okay, I think we'll wrap up and head to the next speaker.